Good afternoon and welcome to this webinar provided by bobwillis.co.uk. My name is Bob Willis and I'll be presenting today's webinar. Before we start talking about the webinar today on conformal coating, I'd first like to introduce you to the control panel, which you have on your screen at this moment in time. Now, the control panel allows you to do a number of things during the presentation. First of all, you can open and close the control panel, thus it not obscuring your view of the slides during the presentation by clicking on the orange button. You can make the image on your screen or on your projection facility go full screen by clicking on the button as indicated here by the red arrow. Now, at any time during the presentation, you can ask a question, and all you need to do is go to the question in the control panel and type your question. We'll be answering the questions at the end of the webinar this afternoon, but sometimes you find it easier to type a question while you think about it, or it relates to a particular topic or slide. So just type the question directly into the control panel and we'll do our best to answer it at the end of the webinar this afternoon. Now, if you have any technical problems, please use one of the telephone numbers provided on your registration and reminder emails. You'll also need your webinar ID number and access code, which was included on your email. It's not possible for the presenter to assist you during a live presentation. Please also remember the internet is still under considerable pressure and you may have some local speed issues in your country, your area, and possibly even in your own factory if everybody's watching YouTube at lunchtime. This webinar presentation slides will be sent to you shortly after the end of the webinar. Please make sure you check for it. Also check in your junk folder just in case it's crept in there. We have a couple of survey questions at the end of the webinar. If you just like to take those, answer those questions, it's good feedback on the content of the webinar, topics you'd like to hear us present in the future, and a number of other things. So if you just take a few moments, that'd be really appreciated. And just a reminder, you'll be getting a copy of the presentation slides shortly after the webinar this afternoon. So a little bit about my background before we start. I've been involved in electronic manufacturing and mechanical engineering all of my career of pretty much over 40 years. I've been involved in providing training online and theory and hands-on in factories. I've been running production facilities with companies in a quality role as well as a manufacturing role, and I've worked in PCB fabrication, assembly, environmental test, and failure analysis. So that just sort of gives you an idea of where I've been, what I've done in different countries all over the world. So that's a little bit about me, and let's move on to our subject of today. Now, some time back I created a guide on conformal coating defects, and you'll be receiving a free copy of this with the slides. So again, hopefully that will be useful to you as a reference guide when you're looking at conformal coating or possibly training other staff. So that's just an extra thing that we're including for engineers on this webinar. So first of all, why do we want conformal coating? Well, it potentially prevents premature failure of product. If a product is going to be operating in a condensing environment, something where moisture can evaporate and condense onto the subject, then having some sort of protection coating is beneficial. If a product is being operated in an environment where you've got toxic chemicals, other gaseous forms of corrosive products, then some conformal coatings, again, may be beneficial to you. It sometimes can be used to improve performance of certain components where that particular component is affected by moisture condensation, fluctuations in temperature, etc. So sometimes people will put coatings just on one specific area of a printed circuit board to give that edge, if you like, to the design. It does provide environmental protection. Now, some conformal coatings are not hard, they're soft, and can allow a product perhaps to be exposed to higher temperatures possibly, or even mechanical shock and vibration. So again, there's a benefit there. It can be used as an alternative to putting a product in a sealed box, and it may well be a cheaper option, but it may not be the right option. So again, you've got to look at both of those options, but certainly it's an alternative sometimes. It can reduce the cost of the end product if you are substituting a coating for perhaps an enclosure, but again, it's very design specific. As I previously mentioned, it can ruggedize the product and improve the performance and longevity of the design in certain situations. One of the things you must never use conformal coating for is to overcome other process problems. So if you've got an issue where you've got some form of corrosion, dendrite formation, change in resistance, capacitance on the surface of the board, and that may be related to your assembly process and the materials you used, putting coating on the top will only exaggerate the problem. It won't overcome the problem. So you need to find out the root cause of your problem rather than just jump straight into conformal coatings. Now, conformal coatings, as defined by the IPC, is a coating which is thin, transparent. It can be a polymetric material that's applied to the surface of the board and the components and their terminations, and typically may range from 12 to 200 microns in thickness. So that is generally the statement within the IPC standards. And of course, you don't necessarily need to have such a thick coating, but perhaps the minimum coating is what you might need for most applications. There are different types of conformal coatings, and again, I've just illustrated some of the more common coatings you'll come across, and you can find these referenced in the IPC 830 specification. So acrylic resins, polymetric resins, epoxy resins, silicon resins, and that's one of the materials that's generally used for more high temperature applications, generally speaking. That's a softer material. You've got fluorocarbon resins, and also you've got parylene. Now, parylene is considered to be the Rolls-Royce of conformal coatings, because if you coat a board, the process used is a gaseous application. So rather than a liquid coating, a gas is forming on the surface. So it really does give you precision thickness control. Wherever you introduce it, that will be the thickness you get all over the surface. So that's one of the benefits of that coating. But again, it tends to be more expensive than the other coatings. So you need to know which option is appropriate. And the best way of understanding that is showing the product, its application, to a supplier of conformal coating, and they will be able to recommend which is the most appropriate one for your particular application. If you want to look a bit more into coatings, there's a couple of books available, and I've listed the specifications and also illustrated the standards and one book which is available. So again, when you get a copy of these slides, you can research it and see if you think there's something that might help you and your colleagues with conformal coating. At this moment in time, the best book on conformal coatings is this, written by Manfred Super. He's an engineer from Werner Peters, and this book was written by himself and a couple of other engineers, and it really is the best book that's currently available in the industry on conformal coatings. Again, you can search online for where you can source that book. So a little bit of background in terms of survey results. These are surveys that I do quite frequently on my webinars, and it's useful to try and understand what other engineers think. So in this particular survey, it was around about 100 people. What was the number one problem, or the main reason why people were conformal coating? And it was corrosion and dendrite formation. That was number one. And then next one, electrical specification, so improvements on that. But number one was related to corrosion, moisture condensation, etc. In terms of what coatings are most frequently used, of course, it depends on who you ask, but this is, again, responses back from 100 engineers that were involved in the webinar. So 37% were using acrylic materials and 21% were using silicon and polyurethane for 27%. So the Parylene and epoxy coatings, again, maybe the high reliability military market, smaller percentage of the pie, but it gives you an understanding of the prominence of certain materials within the industry. So what are the most common problems that people faced with conformal coatings? So if you're already doing it, what are the problems? Well, it's broken down pretty much into three. Most common is variation in thickness of coating, and that comes down to the application and whether you put one coating layer on or multiple coating layers. Bubbles in the coating, so voids in the coating, and non-wetting of both the PCB surface and or the component itself. So again, that sort of gives you a feel for the problems that are faced. And we'll try and pick up on most of those during our session today. So first of all, methods of application. Well, one of the simplest ways is dip coating. So we have a container full of a conformal coating material, those that are appropriate for dip coating. We take our printed circuit board, which is fully assembled, and if there are areas on the board that mustn't be coated, then they need to be masked. So that's a separate operation. The board is then lowered into the container, the tank of conformal coating material. So in this video, you just see an example of a board assembly going into conformal coating. So it would go into the coating and then slowly be lifted out of the coating based on the process that you're going to be using and the thickness of the coatings you want to achieve. So after a period of time, the board would then come out of the tank. The key thing here is allowing any air to escape from underneath components. So the coating is displacing everything on the surface of the printed circuit board. But if you don't allow air to escape, then you could get voids and you won't get consistent coverage. So again, it's experimentation to get the process right. Spray application can be all over the surface of the board, as we see in this particular example. So the whole of the board is coated. But it will depend on what is critical to you in terms of the coating and the coating thickness using this type of application. Because depending on the shape of the component, the shape of the leads, then a coating process like this may not give you what you need. You might need to go to another process. A simpler process is brush coating. Now, it's perfectly feasible to do brush coating, but generally speaking, brush coating is used after some rework and repair. So you've already coated, you've reworked that area, you want to recoat, or it may be used where you're just coating one or two terminations on the board and nowhere else. And the material you use for a brush coating needs to be considered, because with most coatings having a solvent system, generally speaking, it evaporates. So when you're brushing, it's like painting a door on a hot day with thick paint. It will not tend to be very consistent when you're applying it. So again, if that's the operation you want to use, you need to speak to your supplier on the viscosity of the material being used. You can use manual spray coating. So here's an example of a subcontractor manually spray coating the surface of the printed circuit board. He's basically doing on a rotary cake stand, and all of the areas covered with tin foil. And you'll notice that he's rotating the board assembly. What he's trying to do is achieve an even coating and certainly a coat in all areas on the printed circuit board. So what we're trying to achieve with our coating process, whatever it might be, is a fairly consistent coating. It's coating all the surfaces to protect against any corrosion or damage on the printed circuit board due to the environment it's going into. You want to minimize the possibility of bubbles forming within the coating, which reduces the insulation gap between terminations. And that material must give us some form of or indication that's been applied correctly. And that's why you see in this photograph some optical images under UV light, and more about that a little bit later on. But you can see how the surface tends to fluoresce, and that's one way in which we inspect coated boards. Now, one of the things to bear in mind, particularly over the last few years, there's been a lot of concerns of tin whiskers when we move to lead-free. So any termination that's got tin on it, it can form a tin whisker short. And what you're looking at here is an SCM photograph that was conformally coated, but the sides of this SO package has no coating on. And consequently, what you can see here is a whisker. And these very dramatic photographs were taken as part of an MPL project and also featured in the MPL defect database. But that's a short, a direct short, between two surfaces that were not conformally coated. And you can see it. That's a tin whisker short, very prominent in this particular image. So in terms of conformal coating, whatever material or process you use, it's important that the design engineer or the quality engineer define what material you want, what that actually gives you in terms of material and performance, but also you want to define where you want it and where you don't want it. So normally speaking, when I talk about inspection criteria, you also got to have something which says, I must have it there, I don't want it there, and it doesn't matter if it's here. Now that might sound a bit random, but sometimes, depending on the process you use, you can get overspray. Small droplets can go on to certain areas, but if it doesn't matter, doesn't affect the operation of the product, then fine. So it's those three things: where you have it, where you want it, where you definitely don't want it, and where it doesn't matter. And that's much simpler for your own department or with a contract manufacturer. And I just illustrate an example of one company's specification here as an example. Now, one of the things that you should consider when you're going to be introducing conformal coating, you've got to engineer a process. And you can effectively conformally coat on a board that's been cleaned and effectively coat a board that's been through a no clean process, so no clean. But you must make sure the generic materials are compatible. So the flux residues that are left behind are compatible with a conformal coating. And you must do some form of trials or see the results of some form of trials. Otherwise, you're just guessing. So that's an important thing to do. And to allow you to do that, you'll be able to read in more detail, and this is far too big a subject to go into today, look at using SIR, surface insulation resistance, where you measure the change in performance of a board assembly before and after coating, and when you expose it to a moisture environment. Contamination testing, seeing if there is anything left on the board, if you're going to go for a no clean process, and or the use of ion chromatography. Ion chromatography is checking for ion content, so corrosive materials, but it's actually measuring specific materials rather than contamination like rose testing is a general number of those materials. So you're being specific on what you're looking for. Now there is criteria which we'll mention in IPC and other standards, and of course you need to consider other things that we can do as simple process control checks in the manufacturing environment for conformal coating, which hopefully we'll illustrate today. So first off, adhesion testing. So when you apply a coating to a surface, you want it to stick. You don't want it to come apart. You don't want it to separate off of the surface. So this is an example of adhesion testing which isn't very good. And what we've got here is a special blade tool which has been applied to the printed circuit board you see in the video. And you can see how all the coating is just literally coming away. So the adhesion is very poor. This is called a tape test, and the tape test is defined in a couple of ANSI ASTM specifications. You'll also find it in IPC documents. But It's the adhesion of a material to a surface, and the degree to which that material separates, obviously, you set your criteria based on it. Now, a lot of people never specify the solder mask type they have on their boards, and they don't know. They know it's green, and they know it might meet the specification of IPC, but they don't know what it is. So if you're not in control of that, that's a negative. You, as the designer, the assembler, the quality department, need to know, what is it? Is it a Peter mask? Is it one of the other suppliers that are out there? You need to know, and you need to check the adhesion characteristics with the chosen conformal coating you're going to be using. Finally, what is the impact of no clean? Is a board with a lot of residue going to have the same sort of adhesive characteristics? Probably not. So again, you've got to weigh up whether the performance of your materials is going to be affected by other parts of your process. So as a simple example, another thing is knowing the wettability, the surface energy of the board with the solder mask on before and after processing. So what these are is dye pens or dine pens. They're giving you an indication of the surface wettability of a test fluid. And you buy these, they are graded at different levels. And this allows you to do a fairly simple measurement of the performance of that coating. You'll notice I'm measuring on copper as well as on solder mask. And as you look at the examples here, you can see the one on the right-hand side, which I've just drawn, is not breaking up at all. So again, the wettability of that surface is far superior to the other two. So if you imagine you're putting a liquid coating, a conformal coating material, onto a surface that is a poor surface for that coating, you will never get consistent coating thicknesses on that surface. So it's knowing the material, but also knowing the surface that you're actually using in manufacture. Dine pens like this for testing are somewhere between 30 to 50 pounds, $30 to $50, that sort of figure. There are other ways of testing, but this is one which is quite popular with engineers because it's fairly simple. You can actually measure the surface tension or surface energy of a surface using a fluid and also measuring the wetting angle. And I just show you this as a black and white image or a sort of semi-black and white image. And you can see the surface is different between those two globs of liquid, and you can measure the wetting angle. And that's another way that it's done, perhaps slightly more technical. Now, in terms of coating and cost, and this is sometimes something that a lot of people ask about, what I've done here is I've given you 3 slides, and this is a theoretical, but it's based on practical experience of a board assembly with masking and meeting specifications. And this actually was included in a conformal coating interactive CD-ROM I made a few years back. But I've taken these out just to give you a point of reference because a lot of people ask the question. So you can plug in numbers to this, and you can take these timings as a point of reference, and you can work out the cost of any board. Now, I'm sure you probably have other calculation methods, but for those of you who haven't, it's quite a nice simple example that you'll be able to use. And as you can see here, the final price of that particular theoretical board. And of course, mainly it's labor costs, and mainly it's to do with masking. So if your design team can eliminate masking on a printed circuit board, then that's advantageous. If they can't, then again, that's one of the holdbacks of the process, and maybe the requirement to have a design which allows automated coating in selected areas on a board. But then again, that is a machine costs, and of course you need a good skilled operator to program that machine to do the coating for you. So this just gives you also the cost of materials. Now, this changes all the time, as I'm sure you appreciate. So I've given you some typical numbers per litre of material, for 4 different materials. Again, it gives you a point of reference. Please don't take these as the right cost. You speak to the supplier. He will give you the cost, because it fluctuates for a lot of different reasons, but it's a point of reference at least. Now, I mentioned vacuum deposition at the start, and I mentioned Parylene as a coating technique. Now, both of these examples have been coated with this process. So one of the things I know that when you use Parylene, so you're putting your boards into a gaseous environment as part of the process, you get consistency of thickness. So everywhere on the board you see on the left-hand side, there is a coating, and that coating will be consistent across pretty much every surface that's exposed. So that's an advantage. So you can build up the thickness you require for that particular product. Now, one of the things the traditional Parylene process doesn't have is a UV fluorescent surface. So on the right-hand side, you can see a Parylene coating which does. Now, again, that's less commonly used and it is more expensive, but if you want the ability to inspect easily the coating of a process which is pretty much guaranteed to give you what you want, then again, you pay a little bit more. Some friends of mine say that you can optically inspect for thickness of Parylene. I kind of disagree. I've never been able to do it. Perhaps they're just better than me. I don't know. Now, we've mentioned a couple of times that one of the issues with conformal coating is bubbles. And I just wanted to show you these 2 videos that I made, which just show you a board assembly and bubbles between terminations. So if you imagine you have got coating material around the leads, but a bubble there is air, so the amount of insulating material between those 2 terminations is reduced because of it. You could argue that these will not affect the long-term reliability. The problem is to try and introduce bubbles to check that is the case if you were doing testing. So probably the most common reasons for bubbles is air trapped in an assembly, underneath assembly during the coating process, putting too much coating on at one time, and any bubbles don't have the time to escape. So in that particular video, you saw the bubbles escape, and it only took a few seconds. But if you were to put on one coating and then another coating, or put on a very thick coating, it takes longer for those bubbles to escape. You can also get outgassing from surfaces like board materials. If the board material doesn't wet with coating, it's non-wettable, then you'll tend to find bubbles or separation of the coating on the surface. There are lots of other reasons, but I just highlighted a couple. But these are just nice little video clips just to show you with micro photography a coating which hasn't been cured yet. It's just been applied, but you can see the bubbles in the surface. So just think about that. Also refer to the defect guide that I'm providing to you, which again will give you some other areas of highlight to how to eliminate. So in terms of inspection and quality control, key things, obviously the material itself, making sure that it's in date, it's the right viscosity that you're using, so the right runniness, if you like, or the right solids content. Making sure that the materials we're going to coat are appropriate. Remember I mentioned about the solder mask and of course the components themselves, which can lead to de-wetting on the surface, so the coating not sticking. We've got to prepare the boards for the process, and of course we've got to look at inspection. So let's just talk about a few things that we can do. So one of the simple things we can do is use a wet gauge, a gauge to judge the thickness. Now this is quite simple and crude, but it has been used for many years and still used in the industry. And basically what we're doing is looking at the wet thickness before the curing operation. Now, If it's a solvent-based system, the solvent will evaporate and leave the solids, i.e. the non-runny stuff, to be non-technical, on the surface of the printed circuit board. So again, the thickness of the as-applied coating will be slightly different than the actual coating thickness you've got. I always recommend at the start of a shift using a test card or a test board and running the program and doing a QC check on it and compare the performance based on solids content, temperature, nozzle type, speed of operation, all those parameters. And these are pretty simple ways of doing an in-process quality control check. So let's just pick up on that. So if you look on the right-hand side, I'm indicating here, and these other two gauges, these are what we call wet gauges. So the little teeth on the surface are at different heights, and what we're going to be looking at in a moment is the coating on those, and that will indicate the height of the wet thickness. The gauge on the right top left, is a dry film gauge. It's a gauge that's basically working by eddy current. So you're looking at the surface and how far that is away from a metal coating on the base of the printed circuit board. And we check it with a calibration slips to make sure we're getting an accurate reading. But that's for dry, so it's after curing. Now, again, that's a sample check on a flat surface, not on component terminations. But again, if you were to do that as a regular check, it's better than not doing anything. So conformal coating, here's an example. This is a test board that was being run at Henkel, and you can see the coating under UV light. And what we've done is with this wet film gauge is we've offered it up onto the coating, and then if I lift it off the surface, you can notice there are 1, 2, 3 points which are glowing under UV light and one at the end. So the height difference between the one that's coated and non-coated gives you an indication of the wet thickness on the point of contact on the printed circuit board. So again, it's something that is used in our industry. It's not the best, but it's better than not doing anything at all. Thickness measurement, I mentioned just a moment ago, and this just shows you an example of it in close-up, but also we're doing a check and calibration. So the colored slips here are a defined thickness. You can see them marked on here. And we've got a metal surface, so we're actually checking the thickness. So you can see here that we've zeroed it on the metal, and then we've gone on to one which is 54 microns, and miraculously it's 54 microns on the gauge. And trust me, I did the photographs, it really was 54. But you know, if it was 53 or 55, we're not going to worry about a micron, I would personally suggest. But again, it was 54. Now, microsectioning is another technique to look at coating and coating thicknesses, and you will find with the majority of coating materials, they are inconsistent around sharp corners, around bends, on flat surfaces, etc. That is not true of parylene coating, but it is true of most other liquid coatings. So you can improve the performance with different materials, with different viscosities, so different solids content if you like, but fundamentally there will be a difference. So what you can see here is on the sharp corners of these microsections, on the tips, there is a coating or a non-coating present, and you can see how it thins out on the edges. So, you know, that's typical. And if you go back to the example I showed earlier, the NPL example of tin whiskers, you could see that the surfaces on one surface was exposed, and that's why they saw that tin whisker. So again, if you think about a spray coating, if you're spraying from one side and not both sides, that's one of the reasons that certain surfaces on the terminations may not be coated. So it's up to the engineer who's defining the program for the coating system to overcome that. With dip coating, as you probably appreciate, the material is going to coat everywhere, but then again, you've got to have masking, which is very dependent on the time required for the process. Now, inspection, I've already mentioned UV light. You can buy UV light systems to add to other inspection equipment. Most of you will probably have seen the Mantis system, as you see on the right-hand side. There are other pieces of equipment you can use, or you can just use a simple handheld UV light source, which I've got here on the left-hand side. So these are techniques that you can use to look for conformal coating on the surface of the printed circuit board. Now, another technique you might consider, I know I have been reprimanded, I've been told off for suggesting this, but it works. And again, this is quite a simple and crude method, but again, I've used it and it works. It only gives you an average number on the surface of the printed circuit board, but that's better than no quality control at all. So basically, what I do is either put a marker, a sticky label, if you like, a round sticky label, a square sticky label, perhaps on the scrap areas of the board, or actually on the board itself, put it through the coating process and curing process, and then after you've done that, you remove the dot or the square and measure the height difference between the coated area and the bare area where the tape was applied. Again, that will give you a measurement which will give you the average measurement taken over a period of time. So you can do this as an assessment. So, I mean, that's quite crude, but it works. And you can buy fairly inexpensive microscopes with measuring gradicules to measure height difference as they go in and out of focus. So again, that's something that is fairly easy to do. If you really want to go old school, you could take the dots off and measure the difference between the dot or the square tape and with and without conformal coating using a micrometer. But remember, that depends on the hardness of the coating material after curing, because you will possibly crush it during the measurement. But with care, that can be done. Not the best method, but it's a method and better than nothing at all, as I have said on a number of occasions. Now, in addition to this type of technique, there are other things that we need to consider. If you're going to cure your materials on a board, rather than just allow them to naturally cure or in a box oven environment, if you've got an inline process, then you'll have to measure the temperature just like you do with curing, just like you do when you're reflowing solder paste. We do profiles, do the same thing. But if you're using a UV material, so using a UV tunnel oven, then you've got to look at the output performance of the UV lamps. How they change over time will have an effect on the curing, and also the amount of condensation onto those lamp surfaces and reflectors. So again, you need to do the checks on the machines themselves. Again, they'll be recommended by the supplier what should be done as an ongoing process. And finally, one of the things I think is important, always to have some form of golden board, a reference sample, so you can compare what you're producing today with what you produced yesterday. That's a very useful exercise. So here's an operator just doing manual inspection of conformal coating. It's quite a large assembly. It's not very exciting, but you can see the areas that are coated and the areas that aren't coated are pretty much visible. So again, it depends on how you want to apply, whether it's coated the whole board, but you're using masking to protect those areas that we don't want coated, or we're using an automated process. It very much depends. Now, I mentioned, and again, this is something to talk to the supplier about, if you're using material in a dip coater, particularly, you want to check the material, its solids content, and its viscosity. And this is a methodology which is used, and basically you've got a cup here with a known volume of material, and it runs through a hole at the bottom, and you time it. And the supplier of those materials will tell you what to do, how frequently to do it, but it will also give you a graph to look for the guidelines on what to do if it's outside a specification. Again, this is something that does happen with solvent systems. As solvent evaporates, viscosity changes, so consequently the performance of the material in its application will also degrade. I mentioned about spraying onto boards or spraying onto test cards, and this is a test card that Nordson have used traditionally to demonstrate successful setup of a machine and all the other parameters like nozzles, etc., and record the information. So what you can see here are parallel lines. You can see that you've got thin lines and wide lines. So basically you would repeat a pattern and do that start of a shift. You might do it the start of each shift, or you might do it after calibration, changing materials, changing parameters. So you've got something as a point of reference. And again, if you move to this one, we're looking at a coating which is a clear coating, but it's got a UV trace in, as opposed to the red coating you see in the top example. So again, both of these give you an indication. And because of the marked out square pattern, it looks for and demonstrates any overspray that you might have got. So with the color red material, you would see that pretty easily. So it would just be splattering at the edges. It wouldn't be a nice defined line, which is what you want your process to actually achieve for you. Now, remember that when you're spraying, we're spraying onto an uneven surface. So sometimes it's much better to check the performance on a flat surface that the machine and material is performing correctly, because it may not perform on a real board, but you want to make sure the machine and the material is performing first of all before you investigate what you can do to overcome a problem on a board. If you don't know the process or materials working, you can't correct it on a real board. Now, in terms of inspection, IPC 610 has criteria for inspection, and as you're aware, there are 3 grades: level 1, level 2, and level 3 for products. Level 1 being consumer electronics, level 3 being high reliability products. And if you look through that specification, it will define what is required, what is the minimum requirement, and what are some of the defects, which are process indicators, things that may or may not be acceptable in the manufacturing process. And what I've done is just listed for your reference. We're not going to go step by step through this, but you can refer to it. So let's say for level 1, 2, and 3, target condition for coating is no loss of adhesion, no voids, no bubbles. So that's the target, that's the ideal, that's the best. And then acceptable would be what is acceptable without the necessity to rework and repair. And then we would have the defects, what is unacceptable on a product, shipping to one of those standards for a customer, and what needs to be rectified. Again, just like when you're looking at criteria for solder joints, etc., same sort of thing would apply. There is also inspection criteria which is available from NASA. Now, this is free actually, so if you do a search online for conformal coatings, NASA specification, or conformal coating inspection standards, you'll find a big document, and within that document you'll find specific criteria. So again, you can source this. It comes as a PDF which you can download for your reference. So that's nice, it doesn't cost you anything, but I have to say the IPC standards are the standards most commonly used in all contract manufacturing across the world, really, and most people refer to it. Although there are others, it's still the IPC standards that most people either define or require on their products. Now, another thing that we can do when we've coated a printed circuit board, we can do automated inspection. And you'll find that the majority of AOI companies, automatic optical inspection companies, now have the capability of doing automatic inspection. And certainly at Productronica this year, a couple of other companies have an addition to their platforms they can add if that's a requirement. And a lot of automotive companies and medical companies are now introducing or requiring their contractors to use AOI, automatic optical inspection, for conformal coating materials. So the first thing that has to happen is you've got to have a coating which can be seen under UV light, and that's generally readily available, apart from the one exception I said about the Parylene coatings. But with Parylene coating being so consistent in terms of thickness, you probably would not need to do that. But for most other applications, automatic optical inspection. So you would set up criteria or use the criteria that exists on the software and then scan boards. And as you can see here, an area has been defined and the system would then scan the board and then highlight any errors. So you can see an example here of an area which is being highlighted where the conformal coating is not present. Again, that takes time, so don't underestimate the time required to set up a program. Just like with AOI, SPI, any other automated inspection technique, you need time to set them up and get them right. But when they're right, you'll only get rejects highlighted that are real rejects rather than the ones that are not really rejects that people skip. So again, that's something else to consider, particularly if you're working for high-end products within the marketplace. So what we try to do is look at some of the materials, the process, the fundamental types, etc. So now what I'd like to do is look at some of the common defects. So to give you examples. Now, most of these are included within the booklet that I'm providing to you, but I just wanted to pick on some and highlight them and discuss in a little bit more detail. First of all, this is an example of coating. It's a satisfactory coating, in my opinion, on a PLCC, plastic leaded chip carrier. Now you can see there are areas that there is starting to be de-wetting on the edges and a slight little bit of de-wetting around the edge of the plastic, but this is not significant, really. Yes, there's a small amount of de-wetting, but it's really not going to have any impact on the reliability of the product, I would suggest. So again, it's just thinking about what's going to affect the long-term reliability of the product. So if we look at this one, this seems kind of strange that you've got a board and you've got a blob of coating over one particular component, which you can see on the left-hand side using the UV light. So in this particular case, the company, the design department, said that I need this particular capacitor coated to make sure it doesn't affect, or anything else won't affect, the operation of this particular product. So again, on this particular board, there were one or two locations where coating had been applied, but only, and when you look at it for the very first time, you think, well, why? And is it necessary, or was it a mistake? But no, it was intended. And if you look on the right-hand side photographs, you can see the coating. The coating is around the parts. You can see it on the side, and you can also see it over the top of the capacitor as well. There are very few small, very small voids within the liquid coating or the dried liquid or cured liquid coating, but that would have no impact on the reliability of the product. Now, poor adhesion is something that we do suffer on components as well as the solder mask. So this is a good example of poor adhesion. Now, there is a way of overcoming this, and you've got to decide on whether that's a necessity for you. But first of all, if you lose conformal coating just on the top surface of plastic capacitors, on plastic ICs, QFPs, LGAs, which this is, is it going to affect the reliability of the product? And a lot of engineers won't know, and that's a fair comment. But on this particular example, that's the only area that it was separating and lifting off. All the way around where the terminations were, the sealing, the coating was perfect, all the way around the package. So in my humble opinion, I don't think it would have had any impact on the quality or reliability of that particular product. Okay. Having said that, if you're a customer of a contractor, let's say, you don't know, because perhaps you haven't experienced in environmental testing and all those sort of nice things. But so how could you make it better? whether you need to or not, how could you? Well, one of the things that can be done to clean packages like this is use a plasma. And this is a process which is available with some coating companies. It's basically a plasma. You're creating a plasma gas that's that's attacking the whole of the board, but it's just at the surface. It's just literally doing a cleaning operation on the surface to improve the adhesion. So that's one technique. And if you are really serious, this is a real critical problem to you. The cost of doing this is, insignificant. If this is a consumer product, the cost is significant. So again, you've got to look at that. But plasma cleaning is available from some companies to do that for you. Or you can rent a unit, loan a unit, just to overcome that particular problem. But again, talk to your coating supplier, but also talk to your coating contractor if that's a particular issue with you. Capillary action. This is kind of interesting. And I've made a couple of videos on this particular subject on YouTube, which you can go to my YouTube channel and see. But capillary is where you apply a beautiful coating, consistent to the board, but it actually is drawn underneath the component. So what you're looking at here is not a coating which has been applied manually with a paintbrush around the surface, which it looks like, to be fair. What's actually happened is the coating thickness has been drawn underneath the package. So it's only a thin coating underneath the package, so it's not contacting the top of the body or anything, and it's gone all the way around the leads, but you get this weird drying mark, if you like, around it. And you see it on QFPs. You certainly can see it sometimes on LGA packages, LGA QFN packages, but I tend to see it more on QFPs because you've got a large surface area and the material is just literally sucked in underneath the package, just like two bits of glass. If you put a droplet of water, it capillaries between the two. So again, personally, I don't think it's a real issue. Again, you could just do another coating run on the board and overcome the visual issue, but that's why it's happening. It's capillarying, and if you video it, as I've done in the past, you can actually see it happening prior to finishing the coating process and then going into curing. Okay, corrosion. This is a nice example of corrosion on a product, and this is something you do not use conformal coating to overcome. What's happened here is we've got corrosion and dendrites on the surface of the plastic connector. So if you sprayed this with conformal coating, if you used some fluorinated materials, which are ultra thin coatings, then when you plug a connector into it, it displaces it. So again, you can still get low contact resistance. So that's not so much of an issue. But what's happened here is there must have been a high level of condensation on this particular product because the flux that's sitting on the surface of the plastic has caused the dendrites to form across these two surfaces. So there was a lot of flux and certainly a lot of condensation at some point during the use of this particular product. But you wouldn't use conformal coating really to overcome this. You fix the problem that you've got, which is the application of the material to the printed circuit board. Now, we mentioned bubbles or voids in the surface of coatings, and this is a good bad example, if you like. And really, if you saw bubbles in the surface of the coating like this on the top of this package, it's a QFP package, then again, it's not going to have any impact whatsoever on the functionality or electronic performance of this particular product. However, they are or don't meet the requirement of the IPC standards because there are bubbles there. So, two things. One, the thickness of coating that's been applied to this particular component is excessive. There's no question. I mean, I can tell from here, and I took the photograph, how thick it is. But the point is that the more you put down, the more time you've got to allow for any bubbles, entrapped gaseous materials to escape before the surface tends to dry out, tends to cure, because then the bubbles won't come out. if you've got time for them to escape. But if you put more and more on, you get more and more of a problem. Now, sometimes also, as I said, if you've got de-wetting on the surface, when the coating won't stick to the surface, it's not kind of a bubble, it's more like an area of non-wetting. So you've got a bubble over the surface, but it's forming because of that de-wetting on the surface of the plastic to start off with. So here, in this particular example, it's all about poor control of the thickness of the material. So if we look at this example, again, another good example of bubbles, and you've got them in different areas. One on the surface of a package on the left-hand side, again, same thing. Far too much material on there. However, there's some sort of reaction taking place because you've got a lot of different size bubbles on the surface. So that's kind of strange. You wouldn't expect that from a plastic surface. On the middle image, you can see the coating. So some of the leads are coated, some of the leads aren't coated, and you can see some of the coating is completely forming an insulation material between those pins. So in this example, if you've got a couple of pins which are not coated, potentially you've got the example that I showed you earlier of tin whisker formation could occur. Now, I want to be realistic and sensible here that when lead-free was first introduced and tin became the dominant surface on every type of component that we soldered, there were quite a few cases of tin whiskers. I certainly haven't examined for quite a few years now, probably about 5-6 years, any examples of tin whisker failure. Not saying it doesn't happen, but I haven't seen it or been asked about it. So we may well have got away from the materials, the processing of tin plated finishes that caused that in the first place. But again, there are still a lot of companies that are concerned and use conformal coating as a mitigator against tin whiskers. On the right-hand side, on this, you've got bubbles again, but these are over vias and plated through holes. So we've actually got some volatile material or possibly coating which is sitting in a hole, in a crevice, and it's trying to evaporate and actually cause like a bubble or a void, if you like, out of the hole. So the material is trapped, it's trying to evaporate, or the solvent's trying to evaporate and leaving you with this bubble, like outgassing of a solder joint, but obviously it's not solder in this particular case. So again, controlling the thickness is very, very important. So if we just look at this one, this is poor rework of conformal coatings. Now, we haven't included rework of conformal coatings in this webinar today for you, but let me just mention that for a moment, if I may. What you're looking at here is conformal coating or reworking through conformal coating, which is something I try and get people to avoid doing. It's cheap, quick, and simple, but you still got to clean up afterwards. So both of these examples are, in my opinion, poor rework techniques. So the first one, we're using hot tweezers, which works. You heat up, you reflow the solder joint, pull it off the board, and then you're left with a conformal coating, as you see here. And the same thing on the right-hand side photograph. And that brown deposit is a combination of flux residues and conformal coating discoloration, if you like. So you still got to go in, clean it up. So what I prefer to do when I'm doing rework and repair of printed circuit boards with conformal coating, and this is most conformal coating materials, probably with the exception of silicone coatings, is I like to use an abrasive technique. And basically it's shot blasting. If you imagine shot blasting the side of your house to clean it up, that's effectively what we're doing, but there are 2 or 3 suppliers of equipment on the marketplace specifically for that application. And that's my sort of go-to technique because it's just so simple. It's a clean technique and it really does give you good performance. And then you can remove the components afterwards, after you've prepared the surface for that operation. So again, just a nice example of that. A couple more defects let's pick up on. De-wetting. De-wetting on a surface is normally always handling soils, but it can be contamination from another process. So during the manufacture of a printed circuit board, in certain areas, it may come into contact with other coating materials, other cleaning materials. So it's something which is stopping you coating evenly. If it's a solder mask and you're getting de-wetting over the whole of the surface, then clearly it's compatibility of the material. But remember that we take a board, it may be perfect when we get it, and we put it through processes. We put it through reflow soldering, we put it through wave soldering, we put it through selective soldering. So lots of different processes which could contaminate or change the state of the board. So again, it's being aware at what step does that change in the surface impact your coating. So again, it's experimentation. There's no rule book. It's just looking through your process to see what might have affected it. Okay, so as I said, quite a few different defects, and there's lots more there, and again, lots more in the defect guide that I will be providing for you. Oops, sorry about that. My apologies. So what I'm going to do now is move into Q&A, question time. But first of all, before we do that, just a reminder that if you're interested on our on-demand service, we have quite a large collection of different topics that we cover. And this is just a small snippet of the different topics. And these are all available as a 60-minute or a 3-hour workshop online for your production team or your production engineers or your design engineers. So these are webinars that we do on demand on a date and time for customers. So if that's something interesting to you and your training departments, we'll be more than happy to run those for you. All you need to do is contact us. So moving on to question time, let's see what questions have been asked. So just a reminder, if you have any questions, all you need to do is type the question directly into the control panel, and we'll do our best to answer those questions for you. So let me just pull the questions up, and then we can... Right, so first question. In the dipping video, there appeared to be dust on the board. Yeah, quite possibly. If it's a no clean process board, then yes, that's perfectly feasible. If you don't allow contamination on the surface of the printed circuit board, like flux or flux residues, which is quite common in automotive. I mean, automotive products, 9 times out of 10, they are no clean products. They are dip coated as well. But yes, if you have a requirement and you don't accept any contamination, airborne contamination on the surface of the board, then yeah, fine. It's entirely up to you. It just depends on what you need. Okay, just a comment again. When brushing, go slower, allow the material to flow. Yes, but the point I was trying to make is that if you change the solids content, the viscosity of the material, you will find it better to assist you if you are going to use a brushing technique. But generally speaking, I would only use a brushing technique for rework and repair rather than actually in the manufacturing process. But it's a good point. Okay. What is your opinion or interpretation of standards about the need to coat solder mask? Well, in my opinion, solder mask should never be used as an insulator, although it has insulating properties. So if you've got solder mask, you shouldn't need to coat it. So yes, I would agree with you, or I would agree with what I think you're suggesting. So no, you define, the design engineer defines what is necessary, and 9 times out of 10 is the terminations, the termination pads, and in close proximity to those terminations. when you're talking about components, with certain components, you don't want conformal coating underneath those components. If your product is going to see temperature cycling, a high degree of temperature cycling, and if that is going to happen, then you must make sure that the material that you're using has the same expansion and contraction rates during temperature cycling as the conformal coating material. So everything has to expand and contract at the same time. If the coating expands at a far faster rate than anything else on the board, then you will create cracks and solder joints. So that's why with BGA, as an example, or QFNs, there have been examples of where joints have broken with conformal coating, but only after environmental testing. So that's sort of kind of answering your question and also coming on with another suggestion. Do you have experience with rubber conformal coating? Okay. No, I've only used rubber coatings on one automotive product in Germany, and it was a pretty simple process, in all honesty. And those materials, I can't remember the supplier, but it was coated. It's an inline process, curing. So a tent, you went up to whatever the temperature was. I think it was 90 something degrees C. You stayed there for about 3 minutes, then came down, something like that. Very simple process. And it was that performance they required for that particular product. Okay, that's another good, interesting question. Are there any compelling reasons to coat plastics and other non-metals? Or the bottom line is you've got to think about what impact not coating is going to have on the environment you're going to use it in. So if we sort of step back for a second and say, okay, the most common reason we get failures is dendrites and corrosion. It's going to be those areas where there is a voltage between two terminations. So consequently, if you protect the plastic body of the component and protect the solder mask, that's not going to do anything to protect the joint and those insulated properties you require. A classic example, if I may, is if you take a printed circuit board that you know works, you can power it up and put it into water or immerse it into a salt solution. You won't find a tack on other surfaces. It will just be at the interfaces between the joints, the solder, the pad terminations, and that's where you'll see all the reaction take place. Another thing is Zestron is a supplier of cleaning materials, which some of you will be aware of, but they have a chemical material they use for testing out solder masks, and testing out board assemblies. And again, they apply that to the surface, and they're looking at the reaction time, which is looking or indicating the variation of thickness of that particular mask. And that's a corrosion test, but it's really looking at thickness of the coating. So it's using the technique in a slightly different way. Okay, are there methods to determine the kind of foreign material embedded in a conformal coating? Yes, but expensive. So if you've got something that is in a conformal coating, whether it's flux residue, whether it's metallic, yes, if you go to a laboratory, all of those things can be tested for, but it may well be very expensive. So as a typical example, if I look at corrosion on a board and I think that it might be underneath a component, I don't want to remove the component. What I want to be able to do is get as close to that material as possible. So what I normally do, like on a printed circuit board with a LGA or a QFN, I actually microsection up through the board. So not through the board as a section through the component, but up through the board. So I'm coming up behind the component. I can then see whatever that material you're looking at, and it might be dendrites. I'm not going to disturb the dendrite because I'm not touching it or displacing anything near it. And then I can use other investigative techniques to measure define what that material might be. So if you've got, let's say, corrosion underneath a conformal coating, then what we can do is, if you've got a bubble, so you've got vesiccation, so it's literally bubbling underneath it as it reacts because of the voltage across the surface of the part, and you've got a bubble, you've got a chemical trapped within that bubble on the solder resist. So what I would want to do is I would want to capture some of the fluid inside the bubble and then do some form of analysis on that. So again, that's perfectly feasible. I've done that once myself quite a few years ago, and that clearly demonstrated it was flux, because I could do a comparison between the flux used on production and the flux within the failed sample, and we could do an IR scan, and you could compare the peaks of that scan and show that it was exactly the same material. So it wasn't guessing that it was flux. I could prove it was the same material I was using or the company was using. Is it normal to hate doing conformal coating drawings, or should I see a psychologist? Yeah, I think that it depends where you're coming from. I mean, with conformal coating, you don't necessarily have to do drawings. Obviously, you've got CAD programs to produce a drawing. You're saying that area I want, that area I don't want, that area doesn't matter. I mean, I think that is fairly, fairly simple to do today. But it's doing something, because so many customers, when they talk to a contract manufacturer, don't give them clear guidelines. They may say, I want it to IPC, and then when you get a couple of droplets of conformal coating, let's say on the top of their logo on the board, they get upset about it. Come on, it doesn't matter. But define it at the start of the contract, define what you want. That just makes it so much easier. And I have had this quite a few times when I've worked in companies where you've got production and then a conformal coating department and then the quality department. So you've got 3 different departments, work together, agree, and then work to that same standard. IPC, if we just go back to IPC standards for a moment, they're great, but they have limitations. And sometimes they don't spell out, they're not as clear. So look to enhance them, look to add your own photographs, add something to your specification so it's nice and clear and everybody agrees it. But just do that rather than going back and just complaining about something. It really doesn't matter. So that's all the questions I've had so far. If you've got any more questions, just type them directly into the control panel, and I'll do my best to answer those questions for you. Okay, so a question just come in about rework of BGAs. Well, I don't find it difficult to rework a BGA that's been conformally coated, unless the conformal coating has literally been flooded underneath the part, which ideally you shouldn't do because of the potential for expansion and contraction failures. Because the coating will just be around the outside of the BGA, it will not be underneath. There might be a little bit underneath under the first row of balls or second row of balls, but that's about it. So fundamentally, the removal process is pretty much straightforward, the same techniques. The one thing about any rework of conformal coating is knowing the material, and it's making sure the material is going to soften at the soldering temperatures you're going to use, because you don't want to try and lift the part off and damage the board or damage the solder mask or pad areas. You want to be able to repair it in exactly the same way, whether conformal coating is there or not. Next thing is that smell is an emotive factor. With conformal coating materials, when you heat them up, they smell quite often. And as long as you make people aware of that, there is a different fragrance. It's the same as if you've got a brand new cord solder wire that you put into production. If it smells, you'll find quite a few operators perhaps, oh, I don't want to use that because it smells. So that instantly they're thinking, well, it's different, I don't like it. I'm not saying pressurize people into using something they don't like, but I'm just saying familiarize people with what you're trying to do, what you're trying, what's new, etc., so people are aware. It's just my understanding. And of course, you can obviously check with a supplier whether there is anything harmful. Most conformal coating materials, when they're heated up from a rework point of view, are not a problem, but confirm it with the supplier, and of course look at improving the extraction rate you're using within your operation. So once again, if you've got any questions, just type them directly into the control panel and I'll do my best to answer them for you. So I'm just going to take a couple of seconds break from me talking, just to give you a chance with any other questions. Okay, one question just came in. Were the conformal coating materials acrylic? No, they were an epoxy coating, but I have had acrylic materials, and they don't have to be solid, i.e. epoxy hard. What I'm talking about, there is an expansion coefficient, how much a material expands and contracts as you heat it up and cool it down. So if you go from -20, -50 to +100, 120, as you change your temperature, your material, whatever it might be, expands and contracts at a rate. The same as solder joints, PCB laminates, etc. So if the material you're using expands at a greater rate than the solder joint and the component terminations, which may be copper, then you're putting strain on those joints all the time. So what has happened to me when I've seen this and investigated it, you can use X-ray and you can see the cracks in the solder joint, and obviously you can do the microsections afterwards, but normally you'd be able to detect it with a high-end X-ray machine today. Okay, all right, well, what I'd like to do is say thank you very much for attending this webinar this afternoon. Hopefully you've enjoyed it. Hopefully you found something interesting, useful. I'll be sending a copy of the slides to you very shortly by email, and also including the defect guide that I mentioned. Again, if you're interested in any topics that we offer as our on-demand service, then you can contact us, or you just visit our website and book a session, and then we work out the time and date that's preferable to you. So once again, thank you very much. And as it's the last webinar before Christmas, I'd just like to say Merry Christmas, Happy New Year to all of you. Thank you very much, and good afternoon. Good afternoon.